Hello everyone, so I hope you're doing okay. In this video, let's talk about this ion scattering spectroscopy. Now we have talked a lot of techniques which we can use for the surface analysis. So I'll put the link here for playlist so you can go through this link and see whether is there any particular technique that you might be interested in. Now here in this particular technique, right, the concept, the basic principle would be based on the atomic number. So I will take an example and we will continue our discussion. So let's say you have a sample here, right? Here you have a sample and you need to see the composition of the elements on this sample surface. Let's say your sample is consist with barium, carbon and sulfur. Okay, these are the elements you have. Now the principle is basically, there are some atoms which are relatively larger and there are some atoms which are relatively small. Now what we are going to do is we are going to send in some cations such as helium plus, or you can use neon plus, or even argon plus, right? So we are going to send in these ions and we are going to bombard them onto our sample. So this is our sample surface, right? So there are a lot of atoms on our sample. So there are some are big, some are small. Likewise, this is our sample. This is the surface of our sample. Okay, this is our surface. This is the surface on our sample. So there are various kind of atoms like barium. They are very big. Carbon, sulfur, they are relatively small. Likewise, there are atoms which is different based on their sizes and atomic number. Now, when our cation, right, hits a particularly large atom, right, when our bombarded ion hits a relatively large atom, it will scatter, right? It will scatter with minimum energy loss. While if you have a bombarded ion impacted, like it hits a small atom, right, just like it hits a small atom, then it will have a higher energy loss. So in this case you will have a low energy loss. In this case you will have high energy loss. Why is that? Like, you can relate to this very practical problem. Like, if you take a small tennis ball and throw it onto a wall, right, you will see that the tennis ball will bounce back onto you. But if you use the same tennis ball and hit it onto a, let's say, another basketball, let's say, right, then it will not exactly pop out, right? The tennis ball won't come back exactly, right? It will contribute some of its energy to the basketball and basketball will also move out. So that's the thing will happen here. The ball is too big, so the energy which is given by your tennis ball is not enough to move this out. So instead of that, your ball will be scattered completely outside, completely opposite direction. But in this case, energy is transferred to your to the other object, like the small basketball, and it will also move along. That's what happens here. The energy is being transferred into these small atoms and it will use those energy for movements, maybe vibrations. So energy loss will happen when your ion hits a small object, small atom, just like this case when the tennis ball hits a basketball, because basketball is relatively low in size compared to a ball. This is a ball. Okay, I hope you get the idea, right? So when our ion hits a relatively large atom, this large atom won't move. Instead of that, your ion which has formed the impact, right, it will bounce off with lower energy loss. So when you compare the intensities, right, so let me take another color. Okay, so let's say our initial intensity is I naught, and in this case when your ion hits a large atom, right, it's going to scatter, and the scattered intensity let's take as I1. And the other scenario, when your ion hits a small target, small atom, it will also be scattered but with high energy loss, which means energy is reduced greatly, so it's I2. So now in this case you will see, just like here, the tennis ball is not exactly popping out, it will lose its direction, like the energy loss is there. So I hope you can understand, if every time I1 is greater than I2, intensity of I1 is greater than intensity of I2. So this is what our instrument is doing. Our instrument will calculate the I0 and also it will calculate the I1 and I2, right? Whatever the intensity which has been scattered out from the sample, and then our instrument will form a ratio which is I over I0. This can be I1, I2, maybe like I over I0. This is the ratio which our instrument will be calculated. Based on this, it will give us a result. Now let me say that, now if you have relatively large atoms, right? If you have a relatively large atom, I have told you that energy loss is very low, right? Low energy loss will be happen. So which means this I1, which is formed from the large atom scattering, this I1 is mostly identical to I0, because most of the ions which we are bombarding onto the sample, if it hits a large atom, it will mostly scattered out with the completely good energy value. So I0 and I1 is mostly similar, but when it comes to the I2, you know, in I2 scenario, the energy loss is higher. So I2 is not exactly similar to I0. So when you take the ratio for I1 over I0, right, it's mostly 1. So which means the particular peak has high intensity. So when you have a large atoms in your sample, you will see a high intensity peak. While in this case, I2 over I0, right, I2 is mostly reduced, so which means in this scenario the peak is smaller. So let me draw you a example here. So mostly this is our graph we have. So here we have I over I0, and here we will have E over E0. This is the basal energy, right? Energy of the scattered one and energy of the instead bombard ions. So this is the scattered intensity, this is the initially bombarded intensity. So let's say we have a signal like this. This is particularly 1, right? So these two peaks are mostly similar, right? If you remember, our sample is consists with barium, carbon and sulfur. So these two peaks are mostly similar, but this peak over here, right, it has a high intensity. It has a high intensity. So which means this is relative to the barium, because the barium is there, right? Barium is there. Barium is relatively larger when it comes to atomic number. So when the scattering happens, it will have very low energy loss. So this I1 over I0 ratio, the I over I0 ratio is mostly similar to 1. So energy loss is very low, right? So you will have a high intensity peak for heavy elements. When you have a large amount like barium, lead, like cadmium, likewise. So heavy elements will have a high intensity peak. So this is how we can measure the surface composition, like what sort of metals, what sort of atoms are there on our surface. So this is basically the ion scattering spectroscopy. So this is very important when it comes to the material science, I guess. So some of you may have used this when it comes to your research, but either way, this is very important to know, and also I hope it's pretty much clear. It's not that much complicated compared to the XPS or like our Augie spectroscopy. If you have any questions, please feel free to comment below. I will try my best to answer those questions. So yeah, we will meet on our next video then.